So, just get my notes. Yeah. Okay. So, well, I'm going to be talking about set theory and transformation theory, the basics of the both of them. I'm going to keep away from most of the more mathsy stuff. I'm going to mention it, but I'm not going to go into huge detail about it. I can maybe do another lecture later on that, but I think it'd be better now just to kind of get the basic concepts across, and then once you know the concepts, if I ever do another one of these, then I can go more into the maths or anything like that. So for now, I'm just going to start with the basic stuff. So chromatic scale, everyone knows what that is. So the first thing you do generally when you're talking about musical set theory is just to make things easier to write, make things easier to understand. We just write, we use integers, we use integer notation, we use numbers to describe the notes. The common practice is to put 0 on C, but you can put 0 when you're, say, analyzing a piece. People will often just put 0 on what is the most important note of the piece or the first note of the piece, or on C. It's usually on C. I'm just going to always keep it on C just because consistency. It's easier, I think, to understand. I like to just keep it always on C, but you can put it wherever you want when you're doing your own thing. So, first thing, I'm going to talk about a set. We have a chromatic scale here. If I take any group of these notes, then I now have a set. So I can have a set 0 for 7. So this set is a major triad. It's a C major triad. I have C, E, and G. And you write sets like this. You can choose your numbers. You get the numbers, you get the notes. Okay, so that's what a set is. Sets can have any number of notes. Sorry, someone's typing. Sets can have any number of notes. The whole chromatic scale is a set, or you have the empty set, which is no notes. Which you probably won't find useful in any kind of analysis, but maths, you just kind of have to have an empty set. So the next thing I'm going to say is just to quickly go into modular arithmetic, or counting mod 12. You'll notice here that I have, when you go up an octave, you get to the next C. I've written you could number that 12, but we just number that 0. Yeah, that's cool if you can't keep up. My internet's probably not doing you any favors either. Goodbye. Hope you enjoy it on YouTube after. So what we do is, because in Western music anyway, we consider octaves generally to be equivalent to each other. We consider all Cs to be in some sense the same note. We then also number them all the same. So all Cs in all octaves are written as 0. All C sharps will be written as 1. All E's will be written as 4. Should I move it closer? Or is it just not bright enough? Yeah, okay. Let me just 1 second. Is that better? Okay, there we go. Okay, yeah, if you can't see anything, I can try and move some lights around, make it a bit brighter or easier to see or whatever. In this position, I'm not really able to stand in front of it, so I'll just talk to you from kind of off screen. Okay, so yes, I was just talking about octaves. We number everything in every single note, the same number in every octave. Again, it's just a convenience thing, because Western music tends to treat all octaves as the same. And so when we're doing this, we're numbering in we're using modular arithmetic, counting mod 12. It's like counting on a clock face. If you're on a clock and you're at 6 o'clock, you add 7 hours, then you're at 1 o'clock. You're not at 13 o'clock, unless you're using a 24-hour clock. But we're using 12. No quarter tones allowed for now. Okay, so now this is what I'm just going to go in now very quickly. I'm going to talk about something. Probably this will be the most mathsy thing that I'm going to talk about for this entire talk, and it's just to kind of give some background for why we do things like that, like with the modular arithmetic and some other stuff that I'm going to get to in a minute when talking about set classes. So I'm going to talk about something called an equivalence relation. So if I have two sets, I'm just going to label the sets with capital letters. So if I have a set A and a set B, and I want to say these two sets are equivalent to each other in some way. So I draw a little squiggle, tilde, that means equivalent. So an equivalence relation means that the sets, in some sense, can be treated as the same thing. We can look at not in every single capacity because they're not actually equal to each other, but they share certain properties. And for equivalence relations, those properties are, just had something come up on the computer. Sorry, yeah. Okay, sorry, something just came up. So if you have an equivalence, yeah. So if you have an equivalence relation, you have three properties. You have the property of reflexivity. You have the property of symmetry. And you have the property of transitivity. So the easiest is reflexivity. That means if you have a set A or some element A, it will always be equivalent to itself. Not B. That's pretty clear. It's like something should always be equal to itself, and equality is a stronger form of equivalence. So we say everything has to be equivalent to itself. We say it has to be symmetric. So that means if I have two things, A and B, and I have A is equivalent to B, then I can say that B is also equivalent to A. So, to give an example of something that's not an equivalence relation, if I say that A is bigger than B, that doesn't mean that B is also bigger than A. It's not an equivalence relation because it doesn't work like that. On the other hand, equality, the equal sign, if A is equal to B, then B is equal to A. It is symmetric like that. And the final one is transitivity. If I have three sets, A, B, and C, and I have A is equivalent to B and B is equivalent to C, then I can say that A is also equivalent to C. Yeah, maths, woo. So this means that the property, if I have this line, I can just, instead of going through B, I can just go straight from A to C, if that makes sense. Anyone, just if I'm saying something dumb or not making sense, just send a message in the chat and I'll try and explain better. So if we look at, yeah, okay. So now, the reason why I need to talk about this is the maths part, mostly done, is because we have to talk about things called set classes. So I'm going to try and leave this up so you can just see it. Get rid of this now. Okay, So let's say I have a set. The example that I gave earlier, 0, 4, 7. So I said earlier, this is a major chord. It's a C major chord. 0 is C, E is 4, and 7 is G. Now, we, as musicians in Western music, we consider all major triads to be fundamentally the same thing. You know, we go, okay, well, like a C major triad and a D major triad are really the same thing, the same shape, the same sound, just higher or lower. Similarly to how we say all Cs are the same sound, just an octave up or an octave down. It's still the same fundamental thing. So instead of talking about individual sets like this, what we often talk about is set classes, where we take all sets that are equivalent by a certain relation to a set. So for example, if I shows the set 2, 6, 9, nice. This is equivalent to this, because we can see that every element in here is the same, but just with 2 added. So this is equal to 0 plus 2, this is equal to 6 is equal to 4 plus 2, 9 is equal to 7 plus 2. So these two sets are equivalent. And I could write out the big equivalence relation. Actually, I think I have it here on my computer. I'll just share the screen once I get it up, where I go through what exactly this equivalence relation, like all the steps that there are for two sets to be equivalent to each other. Just one moment while I get it up. Oh no, I did it in a different way. Sorry. Okay. So I'll try and show an example in a minute. Okay, so what I've just defined here, calling all sets that are they're considering them the same if they're just adding a constant to all members of it. That's transpositional equivalence. Because what I'm doing by adding something to all the numbers is I'm transposing it. So I've added 2 to everything here. So I have transposed this set up by 2 semitones. So this is I have transposed the set. These two sets are transpositionally equivalent because I can transpose one to get to the other, and I can transpose this one back to get to the first one. The other form of equivalence that we need to talk about is called inversional equivalence. So inverting a set is this is where you'll need to use the mod 12 arithmetic that I was talking about. So if I want to invert this, inverting in the additive sense. So if I want to invert this, what I can do is I can just make everything negative. So I say this, and I'm like, okay, what note is -4? This is where we use mod 12 arithmetic. We can say that this is 0, 12 minus 4, 12 minus 7. Sorry, I'm getting a bit cramped here. And we can say this is equal to 0, 8, 5. Which I promise the maths is almost over. I'm just kind of, this is just, musical set theory is very mathsy. And a lot of it's not very accessible. This stuff isn't explained in any of the basic set theory books that I've read. If you don't understand anything, just ask and I'll try and explain it better. I'm just going to keep going. So if you can read this, because it's very small at the moment, this set is 0, 8, 5. So if we just rearrange this into ascending order, then we get 0, 5, 8. A little bit. They do a little bit of just throwing numbers at stuff, but I think it's warranted here. But, I have 0, 5, 8. And so if I convert this into normal note letter names, then this is 0 is C, F is 5, A flat is 8. So this means that the inverse of a C major triad, when defined this way, just putting a minus in front of it, is an F minor triad. So we can say that these two triads are inversionally equivalent to each other. Does that make sense? And these relations that I'm describing here, the transpositional equivalence and the inversional equivalence, all follow these three rules. Every set is transpositionally equivalent to itself, because if you transpose it by 0, it's equal to itself. These relations are all symmetric, because if you transpose one way, you can always transpose the other way. And it's transitive, because if I can transpose A and turn it into B, and then I transpose B and turn it into C, then I can just transpose C and turn it into A. And similarly with the inverse relationship. Now, what we define as a set class is all sets that are transpositionally and inversionally equivalent to any set. So to use, I'm just using the major triad for everything here because everyone knows what a major triad is. Just clean this off. Sorry. So if I just choose the major triad, the set class of the major triad is equal to all sets that are transpositions of this set, which means it's equal to all major triads, and all sets that are inversions of this, so all minor triads. So the set class of this is equal to all major and minor triads. Okay, does that make sense? We consider all triads, like all the standard tonal triads, are functionally, in set theory terms, the same thing. You know, this is because set theory was largely derived to study atonal music and things where you don't generally have like one triad meaning something very different from another triad just because it's in a different register, or just because, it's a different scale degree. It's meant to generalize everything, to talk about it all just floating in chromatic space, basically, rather than being a functional part of a non-symmetrical scale. Yeah. And they all have names. All the sets have numbers. I think this is 314. I might be remembering that wrong. If you go to Wikipedia and look up list of all pitch class sets, it has a big list. Yeah, 311 actually, I think is right, because there's only... but anyway, the name doesn't matter. If you go to Wikipedia, it has a big long list of all of them with all their names. There's an algorithm for naming them. It's not just random numbers. There's a reason why it's named the way it is, but that's just a naming thing, so you can have a big list of them. You don't actually need to know. It's of no actual use other than just organization. So there's no point in me listing every set. Just Google it. It's there. Easy to find. There's fun stuff on that Wikipedia page. They also tell you where the sets are commonly used. So they give you, sometimes there's a set that's associated with a piece and they just tell you the piece. It's fun. So that's the main sort of conceit of set theory, is this equivalence, this set class equivalence using transposition and inversion, because this is how set theory tries to analyze things. It's looking at the different... So when you're analyzing a piece using set theory, the first thing you do is called the segmentation. So the segmentation process is when you're going through a piece and breaking it up into the sets. Because a piece might use all 12 notes in the entire piece. Even a very short one, it might just use all 12 notes. And you can't just say, well, this entire piece is the chromatic scale and that's my analysis done. So you have to go through it and break it into parts and say, okay, this section, this repeating figure in the right hand, that's a set. But this like melodic figure in the left hand, you can, if you think that appears separately. So I'm going to treat this as a separate set. And you go through and you label all the sets. That's where the naming comes in handy, so you can keep track of everything you found rather than just randomly writing it out. And you look, and generally the idea is that when you look at these sets, you see that pieces often use a lot of the same sets over and over again in different ways. So the easiest example of this is tonal music. Like most classical music of the classical period, like Mozart and stuff, it's all triads, or triads with a few extra notes floating around. It's music, like tonal music can be, in a very rough way anyway, can be described as music which is based off the set 311, or whatever the actual number is. You know, because this is the primary building block of all of the music. All the parts, everything is made of this. So that's what we call it. And it's this kind of is the reason why people say that in atonal music, you tend to not hear triads at all. People might think, oh, like if you're using every note sort of equally or whatever, triads will pop up. And they do kind of pop up sometimes, but composers often try to avoid them because this set is so heavily associated with tonal music. It's hard to decouple it from that. And so people just go, just going to ignore that one. I'm doing my own thing. I'm using lots of clusters and things like that. And, you know, it's that kind of thing. And this is one of the reasons why set theory isn't super useful for analyzing tonal music, because it kind of just says, oh, your entire piece is 311 and not much else, which is why you use it for atonal music, things that use a much wider variety of set classes in it, rather than just using the same one over and over again. Okay, let's get rid of this now because we don't need it anymore. Yeah. That is the free atonality. Yes, it is more useful for free atonality. This system was originally invented by Alan Forte to use to analyze Schoenberg's, Webern's, and Berg's atonal music that they did before serialism. Because there was a lot of stuff put into serial analysis. People like, you know, Milton Babbitt and people did loads of stuff on analyzing serial music. But people like Schoenberg thought that this kind of music was, in some sense, unanalyzable, other than talking about it motivically. In terms of harmony, he didn't really think it was worth trying to describe. And Alan Forte was like, no, I'm going to describe it. Yeah, get trolled. So yes, it's largely used for that. You can use it for lots of other things. Its use has been widened significantly. Alan Forte himself wrote a very big book. Tone rows are usually written using the integer notation. Yeah, using the numbers for notes, but they don't. I'm trying to think of the way to sort of give the difference. Yeah, the sets are ordered is the main thing. Musical set theory is not dealing with ordered sets. When I write 0, 4, 7, I'm not saying you just have a melody that goes C, E, G. I'm talking about the set of notes C, E, G in a vacuum. You see, I don't have a specific order. I don't have a specific rhythm. I don't have anything. This is just the notes that I have. There's, like, for example, that's why I didn't mention anything to do with retrograde, which is, you know, one of the 4 row forms, basic row forms you have is the retrograde form of the row. Retrograde doesn't mean anything when talking about sets because sets don't have an order. Yes, all tone rows are just the entire aggregate, which isn't interesting. It's not, it's used differently. Like, you use the same notation, and a lot of the tools that were developed for analysis of serial music can be adapted to analysis of freely atonal music using this, and vice versa. But the fundamental difference is that if you were to talk about using serial music, then yes, everything is just the entire chromatic scale, and that's not useful information, really. The order doesn't come into anything in this. So I hope that... though, of course, again, you can construct rows out of smaller subsets. Webern did this a lot, where he just takes a small set and then transposes it around, and he transposes this set four times, and he gets a full tone row, and to get a derived row and things like that. And things like that are, analyzable using set theory. I was just, looking at which was the Webern Concerto for 9 instruments, the Opus 24, a few days ago, and everything in that piece is basically just the 3-note set. What is it? 0, 0, 3, 11. He uses the entire row is made of this set transposed and inverted in different ways. He uses lots of 3-note figures that are just these notes in different permutations and different transpositions and inversions and things like that. So it's obviously, I'm not saying it's useless to talk about serial music like this, because you can analyze it, but that's not the tool it was developed for, if you get me. Sorry, just getting a drink. I'm just waiting because Caterpus is typing. Well, yeah. Now this is something. Okay, so I'm not going to go into too much detail about the end goal of musical set theory. I'm mainly in this, I just want to talk about the basic concepts behind it, like the equivalences and things like that. But to very briefly say it, the main idea behind musical set theory and the kind of end goal of the analysis is very similar to Schenkerian analysis, where it wants to kind of reduce the piece down into being only one thing. So Alan Forte would say that in a good piece, in the same way that Schenker says in all good tonal music, you get, your fundamental line, which is the 3, 2, 1, and the bass going 1, 5, 1. Schenker says that all good tonal music follows this pattern. Melody goes down and bass goes 1, 5, 1. Forte says that in a good piece of atonal music, you generally have one set. Look, I can LaTeX spam a lot of stuff at you. I've got lots of pages on the hard drive, but I'm trying to refrain. Forte says that everything in a good piece of atonal music will often be based on one set, which he calls a nexus set. There's a whole big process you go through to try and find the nexus set. He has a book where he analyzes the entirety of the Rite of Spring using this analysis. I'll put a link to it, and he says, everything in the Rite of Spring is either a subset or related to this one specific set that he talks about. This set appears in every movement. This set is, there's a big long thing, which I'm not going to get into because it's all about this really complicated type of relation called a KH relation, which is much more advanced than just talking about minor triad is the same thing as major triad, which is, I don't want to go much beyond this level at the moment, if that makes sense. I can tell you the books, I have PDFs. Yeah, future talks, I have PDFs, I have stuff I can link. I'll put it together a little reading list after if anyone's interested, but for now I'm not going to get too much into that because this is just kind of a basic terminology and fundamental concepts thing that I kind of want to try and do. The Carter all interval chords, so I'll get to that actually now because, well, yeah, that's related to something else I want to talk about, I suppose. But there's something else I need to do before that. First, before I can talk about those chords, I'm going to talk about intervals generally first. Okay? Okay, so I'm going to talk about intervals now. Okay, so if I have two notes, I'm just 0 and 5. So I can pretty clearly see that the interval, the interval, i.e. the distance in semitones between these two notes, is going to be 5. If I want to find the difference between the distance between two notes in using this mod 12 notation, it's really easy. You just have the second one minus, the second one minus the first one. So to find the distance between 7 and 2, 7 minus 2 is equal to 5. Or now you might be thinking, well, what makes you decide, why don't you go 2 minus 7 equals minus 5? And the reason we do this is, again, because of another equivalence relation. So instead of talking about all the intervals as like intervals, we have an interval of 0 steps, we have an interval of 1 step, 2 steps, 3, 4, 5, 6, 7, 8, 9, 10, 11. We instead talk about interval classes, just like our set classes, where we kind of fit multiple intervals together that share something in common. So the obvious thing to think about this is if I have a note C, or denoted by 0. So if I want to move C to B, then I can move it up 11. Up 11 semitones, so I get 11. But also, if I want to go to B, I can also go down. So I can have 0 minus 1. So that's minus 1 is equivalent to 11 mod 12. So intervals the same, going in opposite directions, can lead you to the same note. And intervals that do that, we treat as the same. So, and again, this follows all the same rules for the equivalence relations that I said before: reflexivity, symmetry, and transitivity, if you talk about this. Under those metrics, going up 11 or going down 1 are the same thing. So instead of having 11 intervals from 1 to 11, we instead talk about intervals 1, which can be 1 up or down, 2, 3, 4, 5, and 6. 2 can be 2 up or 10 down, can be 3 up or 9 down, can be 4 up or 8 down, 5 up or 7 down, 6 up or 6 down. 6 is kind of the odd one out. Tritones are symmetrical. You go up a tritone, you get to the same note as if you go down a tritone. It's cool, So we have our interval classes. Yeah. Imagine not caring about the order of notes. Or the order of the notes doesn't matter. You just have a chord. We don't care about melodies or anything. It's just like, just play the entire piece as one block chord and you've basically done the same thing. So when we're talking about sets, what we do is we have another thing that we talk about called an interval vector. So an interval vector is a series of 6 numbers which describes the number of intervals contained in a set. So again, looking at our major triad. So if I want to construct the interval vector of this triad, I have to look at what types of intervals are in this. So basically the way you read this vector is each place is the number of intervals of a certain size. So this is all the number of intervals of interval class 1, the number of intervals of interval class 2, 3, 4, 5, and 6. So if I look at this set, I look at the interval between these two notes. It's 4, so that's interval class 4. So we have 1 here. I look at this, the distance between these two. That's 1 instance of interval class 3. So we have 1 here. I look at this interval. that's an instance of, well, it's a distance of 7, but as we said before, 7 is the same as 5. It's equivalent to 5, so we have 1 of this. So then our interval class vector, and there's no other intervals to check when there's only 3 notes. When there's only 3 notes, there's only 3 intervals. So then our interval class vector is thus, I think. If I'm saying something stupid and wrong, someone correct me. I don't do I generally just like to think about how you do this rather than actually doing these calculations myself. So if I write a wrong number, and you notice, just tell me. So, okay, so that's a fairly simple example. So let's look at just a larger set. If I take, so I'll just pick, okay, someone pick 5 random numbers between 0 and 11. Write it in the chat. First one to do it will be the example I pick. Nine, 8, 5, 6, 7. Okay, yeah, 9, 8, 5, 6, 7. I'm just going to put that in ascending order. 5, 6, 7, 8, 9. Okay, so again, we have to look at all the intervals. So this is a chromatic cluster because every number is next to each other. So you can see this, 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 and this are all instances of interval class 1. So we have 4 interval class 1s. You can see, because we have 4 semitones interval between each one. Next, we look at the distances between each pair that are 2 away. These are all interval class 2, and there's 3 of them. So we have 3 instances of interval class 2. Again, we go one further. We have 2 instances of interval class 3. And then we do this, and that's 1 instance of interval class 4. Yeah, homometry. That's what this is. It's homometry. And then we have 0 instances of 5 and 6. And this is every interval, I think. So you see, this is how you calculate the interval content of a set. And the interval content, in a way, one way to describe it is the amount of melodic possibilities that your set offers. So, for example, you can see that if you were to use this set to write a melody based on this set, you can see, okay, I have lots of small jumps or really big jumps, but I don't really have any medium-sized jumps. You know, you've got loads of semitones, loads of major seconds, loads of minor thirds. You've only got 1 major third, and you have no fourths and fifths, and no tritones. So you don't have that many options with this set if you want to talk about the number of intervals that you can create using it. Now, obviously, that's still, you have like a lot of different possibilities because there's 5 notes. You'll have a lot of possibilities no matter what, but it's not as diverse as it could be. So the next thing, though, is something that... Can you infer the original set based on the interval vector? No, you can't. There's... I'm just going to get to that after this next thing. There's something called a Z relation, which is where 2 different sets that are not equivalent by transposition or inversion share the same interval vector. There aren't, and they will come up very soon, and you'll see. So, just quickly going to what Caterpus mentioned, which was the Elliot-Carter all-interval tetrachords, I think. I'm just going to make sure that that's the right thing, because I don't know as much about Carter. That was what you were talking about, right? The Carter all-interval chords, yeah. Yeah, okay. Yes, there are several all-interval chords. So I'm just going to talk about the tetrachord one because less notes is simpler. So, okay. But the same thing applies to the 6-note ones, and I'm pretty sure there are 5-note ones as well, but I'd have to check the big list of them to remember that. So the set I'm going to use as an example is this 0, 1, 4, 6. Oh, might need a new marker soon. So if we do the same thing again, we check every pair of notes. So, okay, starting from 0, if we go to 1. So we have one instance of interval class 1. I'm just writing them down here because we don't know if there's going to be more of that one yet. Okay, so we have one instance of interval class 1. We check this. So that is interval class 4. Right. So this is one instance of interval class 4 and one instance of interval class 6. We try again starting from the next note. That's an instance of interval class 3. And 6 minus 1 is 5, so that's an instance of interval class 5. And you can see here, pretty clearly, we've got an interval class of 2 between 4 and 6. So, you can see that this chord is really cool because it has one of every interval in it. And it only has one of every interval. That's why I think this one's more interesting as well than the 6-note ones, because the 6-note one, just because it has 6 notes, has so many more intervals in it. It has a few semitones, there's a few of everything. But this is really cool because you have one semitone, you have one major second, one minor third, one major third, one perfect fourth, and one tritone. Now, there's another set that has this same property. And this is what I was talking about sets that have the same interval vector, but different, but are not equivalent to each other by transposition or inversion. So if I take the set 0, 1, 3, 7. If we do the same thing, you'll find the same interval vector. One semitone, one major second, one minor third, one major third, one perfect fourth, one tritone. So these two 4-note chords have the exact same intervals within them, but no amount of transposing and inverting will turn this chord into this chord. You can't do it like that. And so we say these chords are, they use, the term is Z-related. Originally, in Alan Forte's original conception of musical set theory, the Z-related sets were also considered equivalent. So these two sets would be considered equivalent. But when he finally, and this was when he first published the ideas in a paper in the 1960s, but when he wrote his book on it in the 70s, he changed his mind and decided, no, these are too different from each other for me to call them the same thing. So the Z relation is not considered part of the big set class equivalence relation. These are two different chords. They are numbered. Yeah, so this chord is named 4Z15, and this one is named 4Z29. Yeah. So this is the only pair of Z-related 4-note sets, and the only pair of Z-related 8-note sets are the complements of these. Yes, it does. Like if two sets are Z. See, the thing is, it does, but it's kind of not really meaningful to talk about it because in 12-tone equal temperament, which is what I'm talking about, there are never more than two sets that are Z-related. So transitivity doesn't really apply because there's never a third set. You know, like obviously every set is Z-related to itself because it has the same interval class as itself. And if A is Z-related to B, then B is Z-related to C, then B is Z-related to A as well. But because there's no third set. Now, if you go into alternate tuning systems, I know off the top of my head, I know that in 16-tone equal temperament, you get triplets of Z relations, which is really cool. So you get 3 chords that all share the same interval class, but can't be changed into each other by transposition. And they only appear in triplets. It is... I read about this last year and it's kind of left my head, but basically there is a formula, I think, to work out. And not all numbers have this. 12 has this. I don't think prime numbers have any Z relations. Like prime numbered equal temperaments don't have any Z relations, I think. It's something to do. Yes, I'm pretty sure. I think it's solved, but it could be fun to try and look for it again. And there's a lot of work that people have done to try and figure out how can you turn, like, what operation, is there a sort of generic operation that you can do that'll turn any Z-related set into its other one? And I don't think one's been found yet. Like, there are some things you can do to try and change them into each other, but there's no hard and fast sort of method that will always turn one Z-related set into its Z relation, if you get me. You could just count them. Yeah, just count them. It's easy. Yeah, that is actually interesting. I hadn't... Wait, do they? You share two of the same notes. So you only get 6 notes. You get an octatonic, a subset of the octatonic. Oh, you mean if you build a scale using 2 of them? Ah, yes, yeah. Yeah, no, and I think the interval vector of the octatonic scale also has some interesting properties. And again, on that big list of all sets that you can find on Wikipedia, they also have all the interval class vectors of every set. Which is fun. Now, just some very quick other things. There is a relationship between the interval vector of a set and the interval vector of its subset. Of not its subset, of its complement. So there's a complicated formula for it. It's much simpler when you talk about 6-note sets. In 6-note sets, the complement of a 6-note set always has exactly the same interval vector as the original 6-note set that you're using. And this is the reason that nearly all Z relations are 6-note sets. This pair is the only example of 4-note sets that are Z-related. I think there's only 1 or 2 examples of 5-note sets that are Z-related, but in 6-note sets there's like 20. Yeah. So, okay. So that's pretty much the basic vocabulary of set theory. These are all like the objects that set theory likes to look at. Set theory looks at pieces and sees, do they have all these things? What properties do they have? Is this entire piece just one set transposed and inverted loads of times, or is it lots of different things? Stuff like that. That's what set theory looks at. These are the objects of set theory. You look at sets, you look at the Z relations, you look at the interval vectors of sets, all this stuff. Now, so if I ever do another lecture on set theory, I can talk about how you actually use these in analysis or in composition, the kinds of things that people look for. But for now that I've sort of shown you the building blocks of set theory, I'm very quickly, not for as long, that went a bit longer than I thought it would actually, I'm going to talk a little bit about transformation theory, which is the other music-y, mathsy thing that people like to throw around a lot. So, so first of all, I'm going to explain what the difference is between set theory and transformation theory. The way I actually had transformation theory introduced to me was, transformation, all the music math stuff that you like is actually transformation theory. Transformation theory is looking at music through maths. And that's not actually what transformation theory is. There's a very important difference between transformation theory and set theory. And that difference is that while set theory is looking at the objects, set theory is looking at the sets, it's looking at like the properties of the sets. And, you're obviously looking at how the sets are moved around or changed or whatever, but you don't really care. Like, you just go, okay, that's a transposition. Set theory doesn't really stop to kind of examine, well, what does transposition actually mean? Transformation theory, as the name kind of implies, instead of focusing on the musical objects, instead focuses on the actual process by which these objects are changed from one thing to another. So, for example, in set theory, we talk about the idea of the equivalence. All major triads are the same thing in set theory. In transformation theory, you wouldn't really look at the actual major triads. You would look at how does one major triad move to another major triad. Like, for example, I could write, okay, if I have a C major triad and it goes to a G major triad, I'm not looking at the actual triads. I'm looking at this function in the middle, the thing that moves it from one to the other. I can call this the dominant function because it sends one triad to its dominant triad. You get it? It's not looking at the triads themselves. I don't really care about what the triads are. I care about what this does to them. Rather than set theory, which is looking at the object and the properties of the object for its own sake. Yeah. What do you mean significance? Was there a significance to C major being F minor inverted? Well, kind of. That the fact that C major inverts to F minor is sort of relevant. Yes, that is the negative harmony. That's because negative harmony is doing set theory inversion, basically. Yeah, like negative harmony is all inverting it's all inverting intervals using the same thing. It's like that's what it is when you're, so for example, like the major third, minor third, but down, and that's the same idea as where dualism comes from, that Riemann would talk about. So Riemann would talk about like how you need, when you're talking about a minor triad, the real root of a minor triad is the fifth. So if I have C, E, G, the root is C. Oh dear. But if I have a minor triad, C, E flat, G, then the root is actually G. Because it's a major third and then a minor third, just like this is a major third and then a minor third. And that's like, that's the idea, that's where dualism comes from. And, that's the significance, I suppose you'd say. It's not, in set theory, it's not really relevant other than the two things are related to each other. But it is, like, this kind of method of strict chromatic inversion is where negative harmony comes from, like the original idea of it and all that kind of stuff. Because negative harmony, originally, the idea comes from inverting voice leading stuff like, instead of your leading tone rising a semitone, what if the leading tone fell a semitone and instead of going to the root, it went to the fifth and things like that. Does that make sense? Yeah, okay. So that's where that all comes from. Yeah, I learned all about negative harmony while studying set theory. It was cool. So back to transformation theory. So, like I was saying, transformation theory is about looking at the transformations. And the most famous, the simplest transformation that most people would understand is transposition. If I'm transposing something, I'm transforming it. My transposition, if I just label it Tn. So if I take any triad, if I take, if I take a C major triad, and I transpose it by 5, then I get an F major triad, because I've transposed the entire C major triad up by 5. And so the transformation is this, the transpose up by 5 transformation. Or you could call it a subdominant transformation, because it moves a chord to its subdominant, assuming that the chord you put in is the root. Or you could name it whatever you want. Now, probably the most famous transformations, which is what this lecture was going to be on before I stole it from SVO, are the neo-Riemannian transformations of P. Let me see if I have a better marker. Is that easier to read? No, that looks way harder to read. Okay, no, I only have 2 markers. Have to use this black one that's sort of running out. I'll try to write less. So we have the P, L, and OR transformations, which are the Riemannian transformations. So P is for parallel. It changes a triad from its major to its minor and vice versa. So P of C major is C minor, P of C minor is C major. Or is the relative transformation. It turns a major triad to its relative minor and a minor triad to its relative major. So the OR triad sends C major to A minor, and it sends A minor to C major. And then you have the L transformation, which unfortunately uses a German word that I can't pronounce. The Leitonwechsel. It's the leading tone transformation, but no one calls it that. They all use the German word. What this does is basically swap the root of a major triad for the leading tone of that key. So it changes C major to E minor, and it changes E minor to C major. It basically changes the major 1 to its 3 and the 3 back to the 1. So, okay. Riemannian. So how would the parallel and relative transformations work with chords without major or minor qualities? They don't. Riemannian transformations were specifically designed to look at triadic music. You can mess with them, and there are generalizations of them, which I'll talk about very briefly at the end, which do work with other things. But as they were originally envisioned, these are just for triads. They just talk about triads. I'll explain later about how they move in between them, and how you can generalize them to other chord types. You can use them. You can use the basic ideas of this talking about any set class, but these are designed specifically to talk about the set class of major and minor triads. They don't even work with diminished triads. They don't work. They're not for that. The transformation theory is about looking at how you move between the different triads, rather than looking at, in more depth than that. And you do get to things about moving in between different things. I will get to that, but this is like the first form of it that was made, which was specifically made just for talking about triads. Okay, so now you can, if you want, you can L a minor chord to get to an augmented. You can do that if you're using them in the neo-Riemannian way and want to only move things by semitones, which that's not what they were originally used for. There's modifications of them, like I said. The original L just went... I think it was OR, actually, that you would change, because P and L both change a semitone. P changes the third up or down a semitone, and L changes a note up or down a semitone. OR is the one that changes a note by a tone, and some people don't like the fact that OR is different, and they make it so that OR moves a semitone. And when OR moves a semitone, you get an augmented triad instead of just a minor triad. And that is how that's something that you do in neo-Riemannian analysis, but this is just good old-fashioned Riemannian analysis. We'll get to the neo in a little bit. If you get me. Okay? So now, if I take any chord, if I take any chord C, then by applying these in the correct order, I can get to any other chord. I'm not going to do that because I don't remember how you find out how to do them, but by applying these in different orders, you can move from any chord to any triad to any triad. It fully it's a transitive. They're a transitive group of functions. You can move to anything using them. But okay, like Catopus was asking, or not Catopus, but like F major 7 was asking, and Catopus seconded. They don't do anything with non-triads. You know, they're all just for major and minor triads. They don't even work with diminished triads because diminished triads are a different set class than the minor and major triads. But there's a generalization of these functions that you can apply to any set class. So now this is very quickly dipping into something that some people probably recognize the name Julian Hook, because I've talked about him a bit, because he's cool. These are called UTTs. No, it doesn't work with seventh chords either. It also needs modification. You can apply what I'm about to talk to seventh chords, and I'll explain how you do that, but just a minute until I get there. So, to explain how these work, first I'm just going to slightly change the notation that I've been using. So, to represent a triad now, I'm going to use a pair of things. I'm going to use a number, and I'm going to use a plus or a minus sign. So, if it has so the number is the root, and the plus or minus sign is whether it's major or minor. So a plus sign means it's major, a minus sign means it's minor. So you can rewrite the P, L, and R transformations in terms of what they do to triads written in this form really simply. So if I have, so let's say I have a root n, so as a variable. So I have P applied to n plus. So this is a major triad on some random root. Okay? So P turns it into a minor triad, but on the same root. So that means we now get a triad with the same root n, but it's now minor. Yeah, UTTs are happening. UTTs, fun. Just very briefly, I wasn't really going to talk about these, but people have been asking about applying Riemannian transformations to non-triads, and UTTs are how you do that. So I'm just going to very briefly talk about them. So same thing, if I apply L on N, the L transformation turns C major into E minor. So it turns a major chord into a minor chord that is 4 semitones above it. So its root is on N plus 4, and it's a minor triad. And then same thing with OR. N plus. So OR turns C major into A minor. So that means that it transposes the root up 8 semitones and turns it into a minor triad. So this equals N plus 8 minus. Now, something that you can do, so this is specifically talking about just triads. However, something that you can see from this, we know from what I talked about at the beginning that the major triad is the inversion of a minor triad, using the set theory definition of inversion, strict chromatic inversion. So I can say that what the P transformation does, the parallel transformation, what it does is it keeps the set on the same root, but inverts it to a different. It applies the inversion to it. So if I take, say, a dominant seventh chord, I'm not going to go through the inversion, but the inversion of a dominant seventh chord is a half diminished seventh chord. So and it's transposed some way as well. But then I can say that the parallel transformation of a G7 is equal to a G half diminished 7. Half diminished the line through it, right? Never remember. Cheat marker. And I can do the same thing. There's 4 semitones. So the L of a G7 is equal to, what's a major third? So that's equal to a B half diminished 7. And the OR of a G7, it goes up 8. Oh, sorry, it doesn't go up 8, it goes up 9. Sorry. Yeah, I counted wrong. That should have been a 9 the whole time, not an 8. So the relative transformation of G7 using this same rule. So we have, what's 9 semitones above G? That is an E. So it's an E half diminished 7. Hello? Stream down? Is it back? Okay. Wait a second. Sorry, I just restarting camera. Let's see if it works. Is it back? Okay, now on my screen it's black, but if you guys can see it, then that's fine. No. Is it back now? Okay, I think it was because my laptop was running low on battery. I just plugged it in and now it's back. Okay. Camera must have turned off because there was very little battery left. Okay. But so you see how you can apply these to different sets. As long as you know what a set is when you invert it and you know how to transpose it, you can apply these transformations in this way. You know, this is a very brief, fast explanation of how you can generalize these transformations. This notation using the root and the parity, the root and which inversion you're using. It's all in UTTs. There's a lot of stuff about UTTs I didn't explain and I'm not going to because they're complicated. Maybe for something in the future, but not for now. I sent you the big thesis that he wrote, didn't I? It's all in there. Oh, am I? My internet seems to be unhappy. Is it the sound that's going crazy? Can you hear me? Okay. So that was very quickly a one way that you can extrapolate the PL and OR transformations to talk about things that aren't just triads. Of course, that method of doing it is still very limited because it doesn't transform triads into seventh chords. It only works when looking at transformations between triads or between whatever set you're looking at. And again, unlike in set theory, where I was saying that in set theory analysis, you're often trying to sort of find what is the main set of this piece. In transformation theory, you're not looking for what is the one transformation that this entire piece is based on. You're looking at it's a much more descriptive form of analysis than set theory analysis is. You're not looking for a specific transformation. You're just kind of observing the different transformations and how they're used. So you can see how something is moving. You can examine look at the transformation of the root movements. And again, something else to separate it from set theory. I've just been talking about transformations in relation to pitch content. That's not the only way you can look at transformations. You can look at how rhythm is transformed. You can look at how anything is transformed. in the book Generalized Intervals and Transformations, Generalized Musical Intervals and Transformations, which is the kind of book that really kickstarted transformation theory around the same time that Forte was coming up with set theory himself. He goes to great lengths to give a lot of examples dealing specifically with rhythm, to kind of show that this isn't just pitch analysis. It's also looking at other things. You can even talk about analyzing orchestration through transformational analysis, or analyzing meter changes through transformational analysis by looking at how things change. Why does one thing change into another thing? Do they change in a certain sequence? Things like that. So transformation theory is very broad, and you can do a lot of stuff with it. And like I was saying before, the thing that separates it from set theory or a lot of other, music analysis is you're not looking at the things. The actual musical objects themselves are not really the important part. The thing you're looking at is how the musical objects change from one thing to another. Yeah, someone's typing a question. Well, just while that's being typed, I guess I'll say that that's kind of everything that I wanted to talk about. I didn't want to go too much into transformation theory because it's so broad, and I know that there is a specifically neo-Riemannian lecture planned at some point that someone's going to do, who's not me, because it's not my area of expertise, really. I know a lot more about the set theory stuff and the UTTs rather than specifically Riemannian and neo-Riemannian stuff. But if anyone has any questions before I log off, specifically about stuff that we talked about. Yeah. Do you want me to, I can go over that again quickly if you'd like. Okay. So what I said was, if you look at the P transformation and you just apply it normally to a triad. So if I apply P to a C major triad, I get a C minor triad. So what I've done here is I have now, when we looked at how do I say this? When we looked at the set theory part at the very beginning, when I was talking about inversions, I said that a major triad is the inversion of a minor triad. Okay? So we have a major triad here. We have a minor triad here. So what the P transformation is basically doing is it's keeping the root the same, but inverting the set that I've put in. So if I want to apply the P transformation to another set that isn't just a triad, then what I can do is I can say, okay, this isn't a transformation. This isn't just something that turns major triads into minor triads. Instead of saying that, I say that it's something that changes a set from one inversion of the set to the other inversion of the set. Because there's only two in 12-tone equal temperament. This might be different in higher numbers, or I don't think it would be. You only have two forms of a set by inversion. You have major triad and minor triad. And I said I wasn't going to go through the process of actually inverting a G7 chord, but the inversion of a dominant seventh chord is a half diminished seventh chord. So I was saying one way you could extend this is saying, okay, the parallel of a dominant seventh is the inverted form of a dominant seventh, which is the half diminished chord. So I said P of a G7 chord is equal to a G half diminished chord, if that makes sense. What do you mean, why? Sorry, Catapus, I'll get to your question after. I'm just trying to explain this first. Do you mean like why am I? Okay, I guess I'll go through the inversion. Okay, let me just quickly look up. Just so I make sure I get the numbers right, because I don't know this one off the top of my head. Okay, so yes, but yeah, okay, yeah, I was just checking something. Okay, so 0, 4, 7, 10. The way we invert something, yeah, SVO's done it. The way we invert something is we put a minus sign in front of it. So we have 0, -4, -7, -10, which changes to 0, 8, 5, 2, which is, if I write it in actual note names, that's D, F, A flat, C. So it is a half diminished chord. Yeah, the inversion of a C dominant seventh is a G half diminished chord. So I say the inversion of any dominant seventh chord is some half diminished chord, and I say the parallel transformation changes the inversion, but it doesn't change the root. So the inversion of a dominant seventh chord is a half diminished seventh chord, and I'm keeping the root as G. So the parallel of a G7 is a G half diminished 7. Does that make sense? It doesn't turn into a minor 7. I don't remember what the inversion of a minor seventh is. Let me just do it actually quickly so I can see. So if I change this instead to 0, 3, 7, 10, so then the inversion of a minor seventh chord would be 0, -3, -7, -10, which would be 0, 9, 5, 2, which is equal to, get rid of that, is equal to C, A, F, D. So it's another minor seventh chord. That's fun. I probably knew that at one point, but I'd forgotten. So minor seventh chord inverts to itself. Yeah, exactly. And so that means if you apply the parallel transformation, as I've extended it here, to a minor seventh, you also get a minor seventh. Hey, sorry. Sorry, someone just came in. Yeah, diminished seventh chords invert to themselves because diminished seventh chords clearly invert to themselves because every interval is the same. So you're just stacking minor thirds up. If you stack minor thirds down, you're going to get the same thing. So that's just, I guess that's something that I should mention. For most set classes have 24 members because you have all transpositions and you have all inversions. But for some sets, as was just shown with the minor seventh, the minor seventh inverts to itself. So that means there's only actually 12 members of the minor seventh set class because it's only the different transpositions of minor sevenths. Inverting it doesn't get you something different. Inversion of a minor seventh is the same as just transposing it somewhere. You get it? And like with the diminished seventh is even less than just 12 versions of it, because as well as being inversionally the same, it's also transpositionally the same. So if I have a diminished seventh chord and I transpose it up a minor third, I have all the same notes. So there's only three unique diminished seventh chords, which is something you learn. That's why diminished seventh chords are good for modulating, because you can fit them in different keys because they share the same notes. It's just the chromatic, inflection, spelling, which is not something that set theory cares about because set theory was made for analyzing atonal music, if you understand. So sometimes these transformations won't do anything if you do them to different chords. Applying the P to an to a diminished seventh chord wouldn't do anything. Also, applying L to a diminished seventh chord, applying or to a diminished seventh chord using that same extension method wouldn't do anything. It would get a different one if you applied L, but it's still just a transposition. It's not actually changing anything else. So, Well, see, those are... the German sixth is just a dominant seventh respelled chromatically, and set theory doesn't care about enharmonic spellings. So that would be the same thing as this. Enharmonics is one of the reasons why set theory is not necessarily the best tool to analyze tonal music. The French sixth is interesting. I think the French sixth also inverts to itself, because it's just two tritones, and tritones both invert to themselves. It transposes. There's a lot of fun symmetry stuff. Like this is French sixth is like a French sixth based on C would be C, E, F sharp, A sharp. Dominant seventh with a flat five, basically. Okay, now, sorry, Caterpus. No, he's gone. Oh, no, you're still there. Sorry, I can't read. So just... No, if it's built on C, it doesn't have... Caterpus, just to get to your question before I move too far away from everything and have to go. So hasn't anyone considered synthesizing them so that inverted sets aren't equivalent, but their different voicings and transpositions are? So this is... that's a question that is one of the reasons some people don't like set theory. Some people maintain that, like, even inversions of sets are too different. Inversions of sets are too different from each other for you to classify them as the same thing. Like, people say that one of the main arguments against set theory is that it generalizes things too much, to the point where it says things are the same when your ear does not hear them as the same thing. Like, and it is something that, you have to think about, is like, do I really hear a dominant seventh chord and a diminished seventh chord as basically being the same chord? When expressed melodically, you can definitely hear similarities, but just played as a block chord, they are very different, and it is kind of something that people fight about. So some people have kind of, done their own thing where they're like, well, I don't think that, half diminished chord, sorry, I don't know what I said that wasn't half diminished chord. What was I just saying? Diminished seventh? Whatever. Half diminished, yes. Half diminished and dominant seventh. So some people have kind of synthesized their own system where they use... they don't use inversion as an equivalence. They only talk about things that are equivalent by transposition, and they talk about transformations between inversions as being different things, and looking at the transformation and the two objects being transformed are two separate things rather than two different forms of the same thing. So you can do that. People have tried to do that. They haven't caught on as much, I would say. Like set theory, most of what Forte said is still the way people do things. Not everything he said, not everything that's in his book is really used today. There's a big section on these types of relations between sets that he calls what are they called? The OR relations, which is ways of saying how closely related different sets are. And that stuff, that whole chapter of his book is completely ignored. No one doing actual analysis of set theory cares about his stuff. Cares about that stuff, but a lot of the stuff that he said is the same. So Dio, inverting and inversion just gives you the original thing again. Oh wait, sorry, you mean an inversion of a core of like a normal inversion rather than a set theory inversion. You still get the same thing, because an inversion, well, like I said, set theory doesn't care about the order of the notes. So, the chord, like the way you've written it is CFA, But in set theory terms, that's the same as FAC. So an inversion will still just give you a minor triad, you know? Yeah, the like harmonic inversion stuff from like your normal harmony stuff, that stuff doesn't matter in 12-tone, not 12-tone, in set theory analysis. You can talk about it in transformation theory. You can talk about transformations that change the inversion of chords and stuff like that, but in set theory terms, doesn't mean anything really. It's not important. So is that okay? Any more questions? I see that most of the people have gone. Yeah, no, I can. I'd like at some point. I'd like to do something that talks more about the set theory stuff, because that's what well, as you can probably tell by the amount of time I spent on it compared to the transformation theory stuff, that's what I know the most about. But you know, I think a basic kind of explanation of transformation theory, and mainly the differences between the kind of approach of transformation theory and set theory, is important for understanding them. So yeah, sorry about the technical difficulties, but yep, I'm done.